Transformer is the first model that eliminated recursive neural network as a seek-to-seek model. By removing RNN, Transformer was able to feed gigantic data set, which led to pre-training with so many sentences in a finite time. In this video, the key equation of Transformer is explained. The input matrix consists of two vectors. The vectors represent different words, I and work, here. Q, K, and V are matrices transformed by multiplying three different matrices with the same input matrix. Now, a vector represents corresponding feature vector that is different from the input vector. This is the key equation of Transformer. The dk is the dimension of the basic vector. You may notice that the equation does not include parameters to optimize. Yes. It is just a calculation. The optimization mainly occurs at the transformation of the input matrix to Q, K, and V. Ignoring the details, the attention is calculated by multiplying Q, K, and V. But wait. Why is multiplying three matrices called attention? First, using the smallest matrices for Q and K, let's think about Q times K. Simply multiplying Q and K results in all possible dot products of input vectors. Note that a dot product of two vectors means the similarity of the vectors, or it means the relations of the original two input vectors before transformation. You can understand the previous calculation with more intuitively with this image. Now you can understand that the multiplication of Q and K is the matrix of all possible dot products. In a translation task, Q and K come from different inputs, such as English words and German. Please keep in mind that each vector represents, let's say, a word, for example. As a result, the final output represents the all possible relations between words across English and German. Next, let's think about softmax. As the name suggests, softmax basically returns max value but in a mild way. The equation is the top left one that exaggerates the max value and returns the same shape vector. Examples are shown in the right. A and B are normal fraction. C and D are the softmax operations. You can see the softmax exaggerates the max values more than the normal fractions. Please note that after softmax operation, the sum of the values in a vector will be 1. Finally, apply softmax to QK and multiply V. For simplicity, set the matrix of softmax simple values. As the image shows, this operation is weighted average of vectors in V. The weights are the four values of softmaxed QK. Remember that after softmax operation, the sum of the vector elements is 1, so in this case, the sum of M and N is 1, so is the sum of O and P. Therefore, you can see that the final matrix consists of two vectors and each vector is weighted average of the two vectors in V. This image visually explains the same calculation. The first row vector in the output matrix is an average of the two column vectors in the V transposed, and the weights are the two top values of the softmaxed QK. As a result, QK indicates the relations of the two sets of vectors in Q and K, and multiplying V generates feature vectors considering every relation to other vectors. In conclusion, Transformer is a model that generates feature vectors explicitly incorporating every possible relation in the element vectors. The point of Transformer is that these weights or relations are automatically calculated depending on the data. In other words, Transformer pay attention to the appropriate relations and the focus is different by data. Isn't that great? In a neural network, weight is directly optimized and the same weight is assigned at the same location, remember? This flexible and automatic focusing enables Transformer to grasp the relations of words, which resulted in understanding language. Thank you for watching.